All right, guys, as a continuation from our previous class where we managed to talk about the laws that we are supposed to understand in our syllabus, working with the Boyle's law and also the Charles law. We have this part, which is very, very important that we are going to check just after talking about this, which is the heating of gases. But this we are going to talk about in three processes that we have. And we are going to have another class talking about the other two, which is the polytropic and the adiabatic. But in this case, we want to talk about the isobaric, the isometric, and the isothermal, but focusing on the heating. All right, so we have got the heating and expansion of gases. Okay, so this is what happens here. We have got the constants that are used, remember, from our laws of thermodynamics. All right, we've got the first law that states about the heat and work are interchangeable, talking about the flow of heat from hot substance to a cold substance. That heat, we talk about that, can be added or rejected, which is going to affect different processes, which is going to be affected with different processes, that is depending with what we're given. So we can have this being heat added or being heat rejected. A heat with a positive value, that is heat added, a negative heat that is rejected. So at constant volume, you will see that at constant volume, we are going to have our Q as mCV times the change in temperature, which is simply T2 minus T1. But here we are going to talk about specifically on each. How do you find the Q on each process? So this is just for you to know about the constants. Constant volume, that is the specific heat capacity at constant volume. We also have at constant pressure. At constant pressure, we are going to have Q is equal to mCp times change in T, where this is the specific heat capacity at constant pressure. And these constants, they are very, very actually important in our syllabus and our simplification. We have got, like I said, CV for the constant volume. This is for the constant volume. We are talking about the specific heat capacity at constant volume there. These are specific heat capacity. All right, this is the specific heat capacity, but at constant volume. So these constants or these specific heat capacities, kilojoules per kilogram Kelvin. That is the units that you're going to have. If it is Cp, this is the one that is at constant volume, at constant pressure, I mean, pressure there, P for pressure, specific heat capacity. Then we also have the gas constant. So this is R for the gas constant. All right, the same units, again, the kilojoules per kilogram Kelvin. You need to understand this. You need to know these parts. All right, then the relationship that we have between R, that R is equal to Cp minus Cv. If I'm given this or this, I can find R at the same time. If I'm given R and this, I can find this one, depending with what you're given there. All right, so we shall talk about this in more detail when we talk about the other processes. All right, but this is what I want you to understand. Each and every part that you have is going to be affected differently. All right, let's talk about the first process that we're going to have in a condition that we have a constant volume. You can have a condition, let us start with pressure, which is fine. We can have a condition where the pressure is the same. We are now talking about the processes that are affecting our gas. So this process is called the isobaric. That is the isobaric process, where the pressure is the same. So talk about the stage 1 and stage 2, it means P1 is equal to P2. The pressure is constant, is the same. So these are the formulas that you are going to need there. Very, very important since the pressure is the same. Remember from our introduction, we said in that condition, we're going to be talking about the Chaucer's law. We're going to talk about V1 over T1 is equal to V2 over T2. Then we talked about the relationship between R and Cp, that is R is equal to Cp minus Cv. Also, we shall talk about the change in internal energy, which is given by mCv into the change in temperature, that's T2 minus T1. And this is measured in kilojoules per kilogram, provided that we have the mass, it is going to be kilogram. If you multiply by the mass, that will be just kilogram, the change in internal energy. So we talked about this CV for constant volume, all right? Then we also talk about the heat that is being added or rejected. So Q being the heat added or rejected for a constant pressure. This will be Cp times the change in temperature, which is T2 minus T1. Also, this is measured in kilojoules. And also, we should talk of the work done, which is very, very important. And work done is given as P1 into the change in volume, which is V2 minus V1. So that's the change in volume. We have got your work done. And also not forgetting for our gas laws, PV is equal to MRT. This is the basic part that we are going to use and relate in our formulas. So now that we have got this, we also need to know relationship that can happen. Q, remember that Q is the sum of the work done and the change in internal energy. So it's something that you are supposed to actually take into consideration or to understand. All right, so like I said, this is supposed to be considered. Let me just write aside here. Remember, I said this is a condition where P1 is equal to P2. And the PV is equal to MRT formula. This one is supposed to be known because it can be used in any process, provided that you've got everything. You've got the pressure, volume, maybe you need T, provided you have the mass and the gas constant. You can use that. All right, then we have got a condition where the volume can be the same. We can have a condition where we've got the constant volume, where V1 is equal to V2. So what is it that you're now considering? This is called isocoric. So this one is the isocoric process, or it can be referred as the isometric process. So this is a condition when we have constant volume V1 is equal to V2. On that condition, that means we are talking about PV being related. Remember from our PV, if we've got something like this, P1 V1 over T1 is equal to P2 V2 over T2. I talked about that in our introduction. So if we are saying V1 and V2 are the same, what does it mean? It means we can just divide by what? By this and this. It cancels. So at the end of the day, we're just going to remain with this. P1 over T1 is equal to P2 over T2 because the volume there is the same. So you relate in terms of what? In terms of the temperature. You now relate in terms of the temperatures. All right, so everything there is not going to change, guys. The PV is equal to MRT. Like I said, this one is a universal thing. So talk about the energy, all right? Talk about the change in internal energy. The change in internal energy this time is going to be given by mCv times the change in T2. Change in temperature, that's T2 minus T1. just like the previous case. And also, we talk about the heat added or rejected Q, which is equal to mCV this time. It was mCP for constant pressure. Constant volume, you use CV. All right, that's going to be into the change in temperature, T2 minus T1. This is kilojoules, provided that you've got a consideration when they say you are using mass per kilogram. I mean, you are using mass as a kilogram. You take your units as kilojoules per kilogram. But when you're just given the mass as it is, you get your answer direct in what? In kilojoules. So that is the idea that you're gonna have in that case. Remembering that V1 and V2 are the same, so that means in the calculation of the work done, if we use the formula, P1 into V2 minus V1, V2 minus V1, that's 0 there, because the volume is the same. So if it is 5 and 5, 5 minus 5, that's a 0. So it means we do not have work done. The work done is going to be a 0 in that case. All right? That's the relationship that you need to understand or to know when you are dealing with your calculations. So whenever you are given this, you need the formulas to apply when there is a constant volume, meaning to say we're talking about what? The process, the isocoric process. When we have a constant pressure, the isobaric process, and also this part of the work done, and we shall relate, like I said, they can be related, the sum of Q, that is the sum, remember, Q gives us the sum of the two. Q is simply equivalent to the work done plus the change in internal energy. All right, so this is what we have. Let us just talk about the last process of this class. Then we take a consideration of the questions, how they might be given, how are they actually given in our simplifications, how these questions will be given. So we have a consideration again when the temperatures are the ones that are constant, they're the same. All right, so when we have a consideration that we have got the constant temperature, we have got the constant temperature. That is a condition when we are referring that T1 is equal to T2. Constant temperature, T1 must be equal to T2. So what are we talking about? Which process is this? That is the one that we refer to as the isothermal process. So whenever they talk about the isothermal process, they are referring constant temperatures, constant temperature. T1 is equal to T2. So it means we can use all those other gas laws. P1, V1 is equal to P2, V2, PV is equal to MRT. I hope you understand that this one, it applies everywhere. PV is equal to MRT everywhere, as long everything is there that you need. All right, so that is the consideration. Talking about the change in internal energy, remember it was supposed to be mCV T2 minus T1, but the temperatures are the same. So the moment you subtract T2 minus T1, they are the same. So I get a 0 there. And if I multiply by 0 anything, I'm going to get a 0. So that means the change in internal energy is equal to 0 since T1 is equal to T2. Since T1 is equal to T2. We use this formula, that's going to give us a 0 there. So that's for the change in internal energy. Then we talk of the work done. The work done can be calculated. The work done actually can be found from the formula P1 V1 into the ln of V2 over V1. So this is your work done, which also remember that what we said here, if this is P1 V1, it means it is equal to MRT1. So it means in place of P1 V1, if you are given mass, you can use that MRT1 into the ln of what? V2 over V1. This formula can be used as also MRT1, but the moment you use the pressure, you interchange it to be P1 on top. P1 over P2. All these as long you are under an isothermal process, you can be able to calculate your work done in kilojoules. All right. Before I say that Q is the sum of the work done and the change in internal energy. So thus Q is equal to the work done plus the change in internal energy, which is a 0 we do not have. So simply Q is equal to what? To work done under an isothermal process. The heat added or rejected is equal to the work done. So this helps you to understand that some of these, if you know these ideas, you don't waste your time calculating something that you know that is going to give you an answer like this. You just have to use the idea of the concept there that is happening. So this is it. That's all. So let us check. According to what we have, the differences that we have here. As you can see, you're supposed to note the differences. If you see each process, you're supposed to note the differences. Okay, let's check what we got here. We are given, let us see our information. That's an example there. We are given that a gas is heated at a constant pressure. At a constant pressure. That means we're talking about the isobaric. Remember our concept. Constant pressure, we are here. So you are supposed to take everything about this part, everything that we hear. These are the formulas that we are going to be using, these ones, under a constant pressure, which is the isobaric process. Okay, so let us see what we have. So the heat is, the gas is heated, all right? So what else we are given? At constant pressure, and that pressure is this. So at constant pressure, it means P1 and P2 are the same. So that means P1 being 689 kilopascal, that is the same as also P2, 689 kilopascal. So it was heated from a volume of and a temperature of from to this, from, this is initially your initial point. So initially our volume is what? We have the volume there, initial. The volume was at 0.085 cubic meters, and the temperature 38, like I said, you just have to add 273. So that's T1. If we add 38 plus 273, that was going to be 311 Kelvin. To a volume of, to this volume, V2, 0.34 cubic meters. So this is what we have. This is a constant pressure. Calculate the final absolute temperature in Kelvin. The final absolute temperature in Kelvin, T2. You need this. So where are we going to have T2? Remember we said this is an isobaric constant. Isobaric processing, where P1 and P2 are the same, the pressure. So we can take advantage of the volume and the temperatures, since we know that these two are the same. So from our V1 over T1 formula, which is equal to V2 over T2, everything we have here. You want to check back and write these formulas so that you'll be able to understand. V1, this is what we have under an isobaric. So I explained everything, guys. Just make sure that you go back to your formulas and understand. So to find T2, you can just cross multiply, then we divide. So this is V1, T2 is equal to V2, T1, that's you're going to divide by V1, divide by V1 this side. So that's T2 is equal to this. So this is what we are going to use to calculate our T2. That's the V2. We have the volume at the end 0.3. 4 times T1. Initially, our temperature was 311 Kelvin over V1. Initially, our volume was 0.085. That's it. So you work with what you are given. So we can find our T2. That is the temperature in Kelvin, which was going to be 1,244 Kelvin. So that was it. Okay. Then the other part of our question was to calculate the total work done in kilojoules. All right, the total work done. So under an isobaric where the pressures are the same, P1 being equal to P2, we saw that under this process, we can calculate the work done by the formula P1 into V2 minus V1, the change in volume. So thus work done is equal to P1. We have the pressure, which is the same as P2, 689, that is times V2, 0.34 minus V1, which is 0.085. That's it. So we are going to have our work done there. That was going to give us 175,695 kilojoules. Okay, so that is the idea there. Just like that. All the formulas, guys, I mentioned there. Then calculate the change in internal energy per kilogram. Given CV, the specific heat capacity at constant volume. Calculate what? Calculate the change in internal energy. All right. So in this case, if the answer is needed per kilogram, it means we are using our mass. This is the idea here. Or I can just erase some of these things, guys, because I just need this space, you see, so that we do not have a challenge. Let me just do this quickly. This is 175.695. We are going to need this somehow. So let us just keep it aside. All right, so this is it here. The question was to calculate the change in internal energy. Like I said, we can calculate this. The change in internal energy is given from the mass times the specific heat capacity at constant volume times the change in temperature T2 minus T1 from that formula that I wrote there. But here it is given that we must calculate, we are supposed to calculate this and get our answer in kilojoules. But they want us to find this per kilogram of the mass, per kilogram, per each kilogram. So once it is like that, it means you are using your mass as a kilogram, your mass as 1. So that's the change in internal energy, the mass, times the specific heat capacity at constant volume, which you are given there as 0.628 kilojoules per kilogram Kelvin, times the change in temperature T2. Remember, here it was calculating T2. We got 1,244. So that's 1,244 minus T1. Initially, we have 311. So this gives us the change in internal energy. And that was going to give us 585,924 kilojoules per kilogram, since we used per each kilogram of the mass. Okay, just like that. Then another part was to calculate the total heat received per kilogram, given CP per kilogram again. It means we are using our mass as 1 kilogram. So what is going to be Q? The total given the specific heat capacity at constant volume. It means we need to use the formula. Remember, we said the Q can be calculated from this formula. MCP at constant what? At constant volume. At constant pressure, I mean. So that's the formula that you're going to take there. All right. So Q representing the total heat that is being received, okay, can be calculated. So we saw that Q is equal to MCP times the change in temperature T2 minus T1. CP for constant pressure, that's why we are given that. So since they need this per kilogram, it means we take our mass as 1 kilogram. That's our answer to be per kilogram. CP given as 0.92 times the change in temperature. Remember our T2, it was 1,244 Kelvin. So that will be 1,244 minus T1 initially, which is what? 311. So that's it. Just like that, we are going to obtain Q. And that was going to give us 858.36, which is kilojoule per kilogram. Per kilogram mass used. Per kilogram of the mass being used. So that's it. That's how you answer these questions. You just have to be careful, know your notes there. I think those notes or formulas that we wrote there are enough for you to understand this. All right, another question, find the work done by a gas expanding. So when it is expanding, it's positive. Whenever it is expanding, you see that for a compression, you're going to get negative answers. So they're saying we are supposed to calculate the work done in this case. We do not know the work done expanding isothermally. So isothermally means T1 is equal to T2. Remember your processes. T1 is equal to T2. From this volume, from V1 of 0.057 cubic meters to this volume, that is our V2 there. All right. The original pressure was, the pressure was 689 kilopascal. Calculate the work done. All right. We saw that under an isothermal process, we can calculate work done in different ways. Work done can be calculated from P1, V1, the ln of V2 over V1. I want you to check those formulas, or we say this can be given as MRT1, the ln of V2 over V1, or it can be given as MRT1, then it will be the ln of your interchange when it is pressure to be P1 over P2. That is how you calculate your work done. So in order to have this work done, we can use one of these formulas. We have P1, yes. V1, yes. V2, yes. T1, no, we do not have, even though they told us that it's isothermal, that T1 is equal to T2, we do not have. So we can't use this unless we are to calculate T1. But from where? That will be another thing again to consider there. So the best formula to use under an isothermal to calculate this work done was this. We have got everything there to find a work done, P1, V1, the ln of V2 over V1. So our answer, you obtain 8 in kilojoules. So that is just substituting your P1, 689 times V1, okay, V1, sorry, that's 0.057 times the ln of V2, which is 0.2 for everything over V1. That was 0.057. So we talked about this formula. Okay, there's nothing that is new there. So this was just going to give you the work done direct, which is 56.458 in kilojoules. That is the idea there. So you just need the information. necessary for that particular question. Formula necessary for that particular question also. So list your information so that you see which formula to use. List the information down. All right, another question that we are given there is that 1 kilogram of gas is expanded isothermally again. T1 is equal to T2. So we have got the mass of 1 kilogram of gas is expanded isothermally from that is your initial point, 0.0566 cubic meters. That's our volume there, to a volume of, which is V2, 0.283 cubic meters. Initial temperature is, that is initially we were at 135, then we add 273, and that is going to give us 408 Kelvin. The CV, that is at constant volume, the specific heat capacity is 0.75 for kilojoules per kilogram Kelvin. So that is what we have. So given that our R is equal to 0.297 kilojoules per kg Kelvin, calculate the work done in kilojoules, not kilojoules per kg, but in kilojoules. Yes, there we just use our masses. It is specifically that our mass is taken as per 1 kilogram. But being also 1 kilogram, so you just multiply by that 1 kilogram. So that's why it will be kilojoules. Not to say it is changing from our last question, no. But remember that we are under an isothermal process. So we are supposed to choose again the formula for work done, and we saw those formulas that I wrote before that we can use to calculate the work done. All right, so there was this formula which was direct. Remember, I said from the formula P1V1, P1V1 ln V2 over V1. We can relate this as MRT1, the ln V2 over V1 again. So this one, we do not have P1. We have to calculate it. We have got V1, we've got V2, we've got, but we do not have P1. So you must calculate P1. So you can use your PV is equal to MRT formula to calculate your P1. But why can't we just use this direct? Because we've got everything. The mass is there, R is there, T1 is there, V2 is there, V1 is there. So the second one is just direct. So the work done from the second formula is going to be the mass of 1 kilogram times R, the gas constant, which is 0.297 times T1. Initially, that is 408 times the ln of V2, which is 0.283, everything over what? V1, which is 0.0566, actually like this. So this automatically gives you the work done in kilojoules. So that was going to be our work done in that case. Just like that. So this was going to give us 195.025 kilojoules. Okay. Just like that. Then the other part was to calculate the change in internal energy under an isothermal. They want you to find the change in internal energy. Guys, this is just a zero there. Remember that from our notes, we said the change in internal energy under an isothermal is a zero. From the concept that the change in internal energy, remember the formula, it's mCV times the change in T, which is T2 minus T1. But remember, T2 is equal to T1. So these two are the same. So if you subtract, we get a zero there. So that's our answer at the end will be 0 kilojoules. Just like that. So that's what they wanted. So that will be 0 kilojoules. All right, another part that we are given, we have got a mass of, given the mass of a gas, which is given as 4.54 kilograms of a gas at a pressure of, that is initially at a pressure of 103 kilopascal is compressed. Take note. So if you compress it, it means your work done will be negative there. At constant temperature, what is the difference between this question? There's no difference because there they mentioned that it's isothermal. They did not write that at constant temperature, but we know that. Now they are saying it is at constant temperature. So what's the difference? There's no difference. We are still under an isothermal where T1 is equal to T. Nothing changed there. Of this temperature, which means that's our T1, which is also our T2. So if we add 273 to 27 degrees Celsius, if we add 273, we were going to obtain 300 Kelvin. So that's the same as T2. To a pressure of, so that is the output there, P2, 724 kilopascal. Then R for gas is given as 0.3 kilojoules per kilogram Kelvin. Calculate the work done in kilojoules. It's an isothermal process with 3 different formulas to be used under an isothermal where T1 is equal to T2. We said work done guys, we saw different formulas there. P1, V1, the ln of V2 over V1, which is equal to M RT1, the ln of V2 over V1, which is also equal to M RT1, the ln of P1 on top this time. So it's going to be P1 over P2. I have got V2, V1. No, I do not have. So this one is going to be complicated. I need to find this. Also this. I have P1 and P2, yes. The mass, yes. R, yes. T1, yes. So this is the best formula to use. So from this formula, that is the best formula for us to apply to determine our work done. We shall see that our work done was going to be from this formula. That is the mass, 4.54 times R there, the gas constant, which is 0.3 times T1, the temperature of 300 times the ln of this P1 over P2. So that's P1, 103 over P2. Our P2, remember, it was 724. And this is being compressed. So definitely our answer will be a negative. So our work done in this case was going to give us a negative 796,795 in kilojoules. That's in kilojoules. So like I said, the negative showing that is just a compression there that is taking place. And on number 2, they want us to calculate the heat received or rejected by the gas. Under an isothermal process or under any process, I say that we can calculate Q by adding. That is, Q is equal to the work done plus the change in internal energy. But remembering that under an isothermal process, the change in internal energy said it gives us what? A 0. And we concluded that Q is equal to work done under an isothermal. So there was nothing for you to calculate. You was just writing the answer, negative 796,795 kilojoules. So here we say the negative on work done is to show that this is under a compression. A compression shows the negative. The negative that we have when it is Q, it is showing that this is the heat rejected. Whenever you see a negative there, it means the heat was rejected. Positive, the heat was being added. Okay, so that was it. That was it. That was a question. Just like that. So you need information. List down your information, like I said. From that information, manipulate to the formula that is best suit your information, there's a formula that will best suit. They can be 2, they can be 3. You pick which one that you want. So you can have also a combination of 2 methods or even 3 methods. Let us see which methods are being combined together here. We are given that a mass of 4.5, so we've got a mass of 4.5 4 kilograms is compressed isothermally from this to a temperature, then it was then cooled to a pressure at a constant pressure. So there are 2 processes, isothermally and constant pressure. These are the 2 processes. Remember, at constant pressure, we are talking about what? The isobaric process. The isobaric process. So there are 2 processes, the isothermal and the isobaric. Isothermal, where T1 is equal to T2. The isobaric is continuing from T2, from stage 2. So it will be stage 2 to stage 3. So there, in terms of pressure, we say P2 will be equal to P3. So this is what is happening. This is what I'm trying to say. The first stage, it was supposed to be a compression. Remember your inputs, 1 to 2. Then we have another part, 2 to 3. So that is the idea there. So the stage 1 to 2, let us just put it this way. The stage 1 to 2 is the isothermal process, where T1 is equal to T2. So at that condition, this is the first stage that you're given, where they are saying it is compressed isothermally from this pressure of 103, initially at P1, 103 kilopascal, and a temperature of 327. So 327 plus 273 in Kelvin, that means we're going to have 600 Kelvin. Then we are given to this, that is the second pressure, to P2. So that's our P2 there, 2068. Then they're now saying at another stage, the gas is then cooled at constant. It is cooled at a constant pressure, meaning to say we are now talking about the isobaric process. We are from stage 1 to stage 2. So we are going to move where we are from stage 2 to stage 3. So that means the isobaric, in terms of pressure, we are saying P2 is equal to P3. Are we not having P2? We have P2 is given. So it means P3 is equal to 2068 kilopascal. All right. What else? Then, and the temperature there is negative 33. So if I add 273 there to Kelvin, if I add 273, that was going to be 240. So we've got the temperature in this isobaric process, T3, which will give us 240. Like I said, it will give us 240 Kelvin. Okay, so these are the stages that we have. Okay. Then let's see another part. R is 0.3 and Cp 1 kilojoule per watt. All right, so we're given R there and Cp. So we are told that R is equal to 0.3 kilojoules per kilogram Kelvin, and Cp for constant pressure, that was given as 1 kilojoule per kilogram Kelvin. So that is the specific heat capacity at constant pressure. So the first question was calculate the volumes at A, B, C, V1, V2, V3. So you need to calculate V1, V2, and V3. The volumes, that was the first question. So if we're to consider there was just something that was direct, because there I can consider that the temperatures are the same, T1 and T2. So it means T2 is 600 Kelvin. So from the PV formula, I can find this. From PV formula, I can find V2. Remember, I have, or from our PV formula, what we want there in this case, or in our question, is to find V1. So that means we're going to have 1, 1, 1. So to find V1, just going to make this the subject. That will be M RT1 over P1. So it's just a matter of substituting our mass, 4.54. So V1 is going to be 4.54 times R, which is 0.3, times T1, our T1, which is 600, everything over P1, that is 103 there. So that was going to give us V1, and that is V1. And in our calculations, we are going to obtain 7.934 cubic meters. That's our V1. Okay, so with the same situation or the same calculation, you see that at the second stage, I have got same consideration, P2, T2, and the mass is the same, R is there. So I can simply use that to find that of V2. So it means V2 is simply going to be mRT2 over P2. It's just a continuation there. The mass does not change, so the mass is fixed. 4.54 times R for A does not change also. T2 is the one, but remember it is an isothermal where T2 is equal to T1. So you use that. So the only part that changed there was the pressure, 2068 now at P2. So that was going to give us V2, which is 0.395 cubic meters. With the same situation, we can use this idea or method to find this, because there's P3, T3, just like here, P2, T3. So it means I can just manipulate to make V3 the subject. Remember, we need the volumes there. We say we're given V1, V2, V3. So V3 was simply going, if I manipulate this, it's going to be mRT3 over what? Over P3. So there we can calculate our V3. So the mass does not change, still at the mass of 4.54 times R also does not change. 0.3, it is the temperature that we now have, which has changed, of 240, and the pressure is still at 2068. So that's it. We are going to obtain our V3 from that. So it is just a matter of making sure that you are substituting your values properly. All right. In this case, all right, that is 240 in this case. So that is the part that has changed, but this one remains as it is. So there your V3 was going to be 0.158 cubic meters. So you've calculated V1, V2, V3, the volumes that are corresponding at each and every point that we are given there. That's V1, which is 7.934 here. All right, so I'm just gonna need this space here, guys. So let me just put it in a way that we can understand here. Then our V2, not forgetting our V2 and V3, we're just gonna rewrite them here so that at least we can calculate the rest of the questions here. All right, so remember, we calculated everything here. Our V2 was 0.395. Then our V3, remember it was, we calculated it was 0.158. Okay, so that was it there. So the question is to calculate the total work done, the total of the whole process that we had combined together. what is going to be the total. So whether it was another process and another process, this is how you answer this question. You combine them differently. We've got the first process from 1 to 2, which is the isothermal process. So the total work done, you combine the work done for the isothermal plus the work done that you're going to have between the stage 2 to 3, between this stage 2 to 3 in the isobaric process, which is the isobaric, or you can write stage 2 to 3. So the isothermal process, how do you calculate the work done? Remember, under you go back to your formulas. Under isothermal, we listed a lot of formulas there, those work done. Under isothermal, remember with P1, V1, the ln of V2 over V1, which gave us mRT1 into the ln of V2 over V1, which is equal to mRT1, and so forth, P1 over P2. So you choose which one is there that you can use. So as you can see, P1 is there, V1, T1. In fact, this one, I can use the first one. So I can even take the first one. Any formula that you can use, as long it is applicable for an isothermal process. So for an isothermal process, we are going to use P1, V1, the ln of V2 over V1. We are going to obtain the work done in the isothermal, plus the work done of the isobaric, this part where P2 is equal to P3. Remember, under an isobaric, we said the work done is equal to P1 into, it was change in volume V2 minus V1. But now take note, we have to be careful about these numbers, because this was from stage when you are just considering from 1 to 2. So this will be P1, V2, V1. But now we are considering, take note of the stage that we are talking about. It's from stage 2 to 3. The isobaric process, it is the one that occurred between stage 2 to stage 3. So between stage 2 and 3, we are no longer having 1 and 2 as we used. So where there is a 2 here, we're going to put it here. So this will be P2, and this will be V3 minus V2 because of the stage that we are talking about, stage 2 to 3. The isobaric process is between stage 2 to 3. So the work done, they use the correct formula there, correct letters. So that was going to be P2, that is the pressure, into V3 minus V2. We are done. So this is for the isobaric. This is for the isothermal. So we are going to find the work done. Then we combine these two. So the first one for the isothermal, P1, V1. Remember, we've got everything there. We're just going to substitute our values. That is our work done will be P1, 103. V1, 7,934, the one that we calculated previously, times the ln of V2 over V1. Remember, we are moving from this to this. So our V2 is, that was 0,395, everything over what? V1, which is 7,934. So this was going to give us the work done for the isothermal process. We add to the work done of the isobaric process between the stage 2 to 3, where we said our formula will be P2. So P2, remember, P2 is what? 2068. So that's 2068 into V3 minus V1, V2, V3 minus V2, 0,158 minus V2. Remember, our V2 was 0,395. So this is 0,395, like this. So this was going to give us the total work, the total of it. So the first one, approximately negative 2,451,628, plus this was going to give us a negative also, negative 490,116. So the total work done combines everything. So that will be negative 2,941, 0.744 kilojoules. That's it. Just like that. So like I said, it is a condition that you deal with. Which process, it might differ with the process, but the ideas that you combine according to the stage, they can be 3 stages. If there was another stage there, you have to add another stage. But the work done for that stage, you're supposed to calculate it properly. So we calculated the work done. Remember the formulas that we had for the work done under isothermal. Remember your formulas under work done for the isobaric. Combine those. So it is the same thing that we are having even on this question, which talks about the total heat received or rejected. So remember the negative there was because it was under a compression for work done. It was under a compression. The question there, everything is compressed. So the heat added or rejected, we're going to check that. If our answer is a positive, it was added. If it is a negative, it means the heat was rejected. But the question is that it is the same thing. It is the same thing. To find the total heat being added or rejected, we need the Q that is between the stage 1 to 2, which is the isothermal, plus the Q between the stage 2 to 3, which is the isobaric. That is the consideration. So how do we calculate Q under an isothermal? How do we calculate Q? Under an isothermal process. Under an isothermal process, remember on when I introduced this, I said Q is equal to work done. Since we have Q is equal to work done plus the change in internal energy, which we saw that under an isothermal energy, the change in internal energy is a 0. So it means our Q is going to be the work done under the isothermal. Remember, we calculated under under isothermal from the previous case, our work done, it was negative 2,451,628. We have that. Under an isothermal, Q is work done. But what about isobaric? How do we calculate the Q of an isobaric? Under an isobaric, remember I said the Q, we use Cp, mCp times the change in temperature. So since the isobaric process is occurring between the stage 2 to 3, the change in temperature is going to be T3 minus T2. So that means we are using mCp T3 minus T2. Final minus initial. The isobaric, the stages there that are being affected is stage 3, stage 2. So it will be T3 minus T2. So this is what we want. So it's plus, let us calculate for the isobaric between stage 2 to 3, we said it's going to be the mass. Remember the mass is given there 4.54. That is 4.54 times Cp. For air, Cp is 1 kilogram times the change in temperature, T3 minus T1. T3, 240, sorry, minus T2, not T1, but T2 for the previous stage. You subtract the previous stage. So that's it. Okay. So this was going to give us, you can combine everything. That was going to give us negative 4,086,028. So this is kilojoules. So the negative that we are having there, it means the heat was rejected. That means heat is rejected. So, or just heat rejected. Okay, that is how you answer this. So there the question is either received or rejected. So a negative, it means it was rejected. So that is it about the heating of gases, and also knowing or understanding your formulas under isocoric, isobaric, isothermal. So we shall have the last two processes, the polytropic and the adiabatic. So those we shall combine again in one class so that you'll be able to understand how to differentiate between the two. Just like this part, you can now differentiate between the three processes: isobaric, isocoric, and isobaric. We said isobaric, isocoric, and isothermal. Make sure you revise the notes. With these, you can answer any question. More to come from Mason African Motives till we meet again.